Hi everyone, welcome back to the channel once again. So in this video lecture we'll try to study about mixing of the audio signal, which is a pure tone signal. Along with that we'll add a noisy signal to it and then find out the resultant signal out of it. So in the last class we talked about defining a sine wave using Python, which is this line of code which defines a sine wave with argument as frequency, sample rate and duration. And for that we use the variables SR as sample rate, time, duration for which the pulse ends is time t equals 4 and the frequency as 2. So let's run this code first to see how the sine wave looks like. So this is the sine wave we got in the last class. Now in this class we'll talk about generation of a sine wave along with a noisy signal and add them together, which would be the mixed tone, and then finding out basically representing the waveform of it. So let's begin. So the very first line of the code, as we can see here, is generation of sine wave with 500 hertz of frequency and the sample rate and the time duration for which the pulse ends. So in this lecture we'll talk about a generation of sine wave, mixing them and then visualizing the result. So let's get started. So the first step is to generate a sine wave. First we need to generate two sine waves. So we are using the function called generate sine wave, which we have already defined in the last class. For this, which takes the frequency, sample rate and the duration. Okay, here is the first sine wave with a frequency of 500 hertz and this sample rate is 50,000, which we have already defined here. We can also hard code if you don't want to call the variable directly. So here sample rate is 50,000 and time for which we want the signal to be available is 4 seconds. Now the next step is generate a noisy tone. So noisy tone, we want to have higher frequency. So we have put up frequency as 5000 hertz. That would be the frequency of the noise tone. The next step is to add them together. So write down the mixed tone would be equal to the sum of signal tone and the noise tone, right? The next step is to plotting this. So plt.plot. And what do you want to plot? Basically mixed tone. So write down here mixed tone. And to show the graph, we need to use plt.show, which will show the graph. Now let's run this. So if we run this, what we get here is this. And this has, you can see on the x-axis, we have value till 200k. But we have not represented, see, we have given the time as argument, okay? But we are not plotting the time. We are only plotting the mixed tone, okay? So therefore, it goes to a very high value. So basically there are many number of points have been plotted here, therefore we can't see the graph of the sine wave clearly. Okay, so what we can do is we can reduce the number of points we want to plot. So for that, in the mixed tone we can use 1000 points to plot this graph. We want only 1000 points. Now let's give it another run to see how the graph looks like. So we can see the graph is something like this. It is quite close to sine wave, so it's pretty noisy, isn't it? So to make this sinusoidal waveform better, we can normalize the signal, or we can reduce the amplitude of noisy signal. To do so, we can add another line of code below the noise tone, okay, right after when we define the noise tone, and decrease the amplitude of it. So what we can say is noise tone equals noise tone into, let's say we want to decrease the amplitude of noisy signal by a factor of 0.3 or 0.4. So let's write 0.3 here. So it may give us the graph better than previous. So you can see initially the amplitude was higher. Now we have reduced the amplitude of noisy signal. Therefore we can see a sine wave better than the previous one. Now what else we can do? So to make this graph better, we have to normalize the signal. So for that we can add the normalization part. So what we can see here is, let's normalize the result. After adding the signal, we can normalize the result. So what is the need of normalization? To make sure audio is usable range, we need to normalize it, and it ensures that our signal uses the full range of the values available for the audio data. So for that we have a mixed tone. This is the mixed tone, right? Each sample of the mixed tone. Now if you divide the mixed tone with the mixed tone max, this step normalizes the mixed audio signal so that its value its value ranges between 0 to 1. Okay, so you can see the range here right now is above 1, right? It's going above 1. So if you want the graph to be between 0 to 1, we need to divide the mixed tone divided by mixed tone max. Okay, so it divides each sample in mixed tone by the maximum value found in the mixed tone. If we want to convert into 16-bit PCM format, what we can do, we multiply this mixed tone divided by mixed tone max with the help of 32768, that is 2 power 16, right? So what does it do basically? The values are scaled up to the full range of 16-bit audio signal, which is from minus 32767 to plus 32767. What we want to plot now is the normalized value. So before that, we need to convert this into integer format. So we can use np.int numpy int 16. So this will help us to convert into 16-bit integer format. So the result of the scaling is to cast a 16-bit integer format. This is the common format for audio data and ensure that the audio data can be correctly processed or played by standard audio tools and devices. This is all about normalization of the tone. Now we want to plot the normalized tone, so we'll remove the mixed tone from here and put it normalized tone. And again, we'll keep the 1000 points to be plotted. So let's run the code again. What we can see here is a signal that contains points, data points from 0 to 1000. And on the y-axis, you see the range. It should go from minus 32767 to plus 32767, which you can see here. This point is mapping somewhere near 32767. So this is all about generating a noisy signal along with the pure tone signal. So in the next class, we'll try to find out FFT, the fast Fourier transform of this, and we'll look at the frequency spectrum of this noisy signal. So thank you for watching. Stay connected to